Hello there and welcome to this collection of notebooks and tutorials on multirate signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato and this is our second notebook, Multiresolution. So in this notebook we're going to see uniform and non-uniform filter banks, and then we're going to talk about the common types of frequency transforms we'll be using. So we'll talk about the discrete-time Fourier transform, we will talk about the discrete Fourier transform, the discrete cosine transform, the Z transform, and the short-time Fourier transform. So let's get started. The frequency decomposition of a uniform filter bank has uniform bandwidth subbands and has the same sampling intervals for all subbands. So here, these rectangles are representing time frequency beams. So we have uniform bandwidth subbands and the same sampling intervals for all subbands. One example of a uniform filter bank is a spectrogram. And we can use Python to plot a spectrogram of an audio file. So here we'll be using SciPy.io WAV file to load our audio and matplotlib pyplot to plot our spectrogram. We import our libraries and make some configuration for matplotlib. We load our audio file using SciPy. We convert this as a stereo. We convert it to mono. Then we plot the spectrogram using most of the default parameters, just changing the number of FFT and the sampling frequency. So here we have our spectrogram with normalized frequency and the time in FFT blocks. We can play this audio file using PyAudio. So in this case we're importing PyAudio and other libraries. We define some parameters. We create a PyAudio instance. We create a stream, and then we convert our numbers that was loaded with the SciPy to a stream of bytes, and then we write these bytes to the stream and we close the stream. So if we run the cell, we should listen . So one of the reasons I chose this audio file is not only is a classic and an incendiary song from AC/DC, but also we can see some things here at the spectrogram, and we can see this percussive sounds in the beginning, and they have this vertical characteristics. At this point here is where it enters the drums with the guitars, and we can see a bit more horizontal structure. These things can be used in a harmonic percussive source separation, so we can have some vertical filters and we can have some horizontal filters and try to separate the percussive sounds from harmonic sounds. It's a very interesting application in a musical information retrieval, and we can see these things by analyzing a spectrogram. Another way to play audio files, is a very convenient way, is using the IPython display. So you pass the name of our audio file, and then it will create this . Gives you these controls. You can also download your file, and it's very convenient if you want to play some files. And we can also plot a spectrogram using librosa, and librosa is a very powerful Python library for audio processing, for music information retrieval. So it offers a lot of functions. Now I'm importing librosa, and I'm loading our new audio file using librosa. So then I am again displaying if we want to play it back. So here we just pass to the display to the audio display the name of our file. Here we are loading our audio file with Librosa. It's giving NumPy array, and we can also play this NumPy array if we pass it to the display audio and we give it the sampling rate. Then we are using Librosa to calculate the short time Fourier transform with 2048 FFT points and a hop length of 256. Then we are taking the magnitude. Here we are normalizing the magnitude. Then we are creating our plot, and we're having our spectrogram. Now I'm using it's not the power spectral density, but it's just the magnitude, and I'm having the y-axis in log. So here it is. This is the classic switch. One of the most iconic guitar introductions in modern rock by Maestro Slash. And I also chose this piece not only because it's magnificent, but also because we can also see some things in the spectrogram. So I chose this configuration. I have the frequencies in logarithmic scale, and I have just the magnitude, not the power spectral density. And we can see mostly here are the fundamental frequencies, so you can almost see how transcription of what Slash is playing. Once again, if we so it gives you a way to see very interesting how the notes are being played, and we can see harmonics, and we can see the fundamental frequencies. So these are two examples of spectrogram. So we have a spectrogram using matplotlib. We play audio, we load audio using SciPy. We play audio using PyAudio. Then we go to Librosa, we load audio with Librosa, we play audio with IPython display, we plot the spectrogram using Librosa, we calculated the short time Fourier transform with Librosa. These are examples of uniform filter banks, same bandwidth for all frequency bands, the same sampling interval, the same time windows for all subbands. Now we have another Python example. We will have a live spectrogram of a microphone signal, and we'll talk about aliasing and downsampling, upsampling, like the previous basic blocks of multirate signal processing we talked about last notebook. At this point, I am importing all the libraries. We're going to use PyAudio again. We are going to use matplotlib. We are going to use Jupyter widgets to have a graphical user interface. We are going to use threading. These are the libraries. Here is the configuration of the parameters we're going to use. So we're defining sampling rate, defining the factor of downsampling and upsampling, number of FFT, overlap. And now we're creating a low-pass filter. We are using SciPy to have this filter. Notice that we have a sampling rate of 32 kilohertz, and our downsampling and upsampling factor is 8. So we remember that we discussed that we need to have a filter 1/8 of the Nyquist frequency of the higher sampling rate. So sampling rate is 32 kilohertz. The Nyquist frequency would be 16 kilohertz. 1/8 of 16 is 2. So we need to have it smaller than 2. I'm having here 1.9 kilohertz. And here we are defining our low-pass filter. And we can see, just plotting frequency response of our low pass filter, we have phase and we have our cutoff frequency at around 1.9 kilohertz. And this is a function that will plot the spectrogram that will get the audio stream, convert it to samples, plot the spectrogram. So this is the function I'm calling run spectrogram. It will be controlled by a button. So we are reading from the stream, getting the samples. If the low pass filter before downsampling is on, it will filter the signal. This part here is a combination of downsampling and upsampling together. So when we downsampling, we are removing number of samples, and we are upsampling, we're inserting zeros in between samples. So when we combine these two, it's like if we're making some a number of samples to 0. So it will be what we're doing in this part here. This is the low pass filter after upsampling. So if the filters will be on, it will filter the signal. This part will play back the audio from the microphone, and this will update our spectrogram. At this part, we are creating our graphical user interface. We are having some buttons to control the start and stop, and to use downsampling and upsampling is on or is off, and the low pass filters. Here we are creating a thread, so we want to run this function inside a separate thread so we can have access to the control buttons. At this point is the usual configuration of PyAudio. We create a PyAudio instance, we create a stream. Here it will initialize our plot and create our graphical user interface. So we will display the buttons, it will display a starting plot. This will handle when we close the plot, what should happen. When we run this cell, we have here our controls, and this will be our live spectrogram. When we start, so we can see our spectrogram. Now we are using the guitar as a signal input, and we are playing a note. When we activate downsampling and upsampling, we can hear and see aliasing. So there are no filters at the moment, but when we activate the filters, we can reconstruct up to 2 kilohertz. If we remove the filters, we can hear and see aliasing again. After the uniform frequency decomposition, the uniform filter banks, we'll just take a quick look on non-uniform frequency decomposition. For example, the discrete wavelet transform, which is basically a two-band decomposition. We have our signal, and we have a high-pass section and with downsampling, and then we have a low-pass section with downsampling, and we cascade these blocks of high-pass filters and low-pass filters with downsampling, and we achieve frequency decompositions with different bandwidth for frequency subbands, with sampling intervals that halve at each step. For example, we can have scaled wavelet. We have there are many types of wavelets. There is the HAR wavelet, the Dobeshi wavelet. You can spend months just studying wavelets. It's very powerful for many applications, but we will not go further. We will not go deeper in wavelets in this course and in this Jupyter tutorials and notebooks. So let's move on. During this course, Professor Schuller adopts notation convention, and we will also adopt in this Jupyter notebooks and tutorials. So we'll use this sign to refer to defined as. So we're defining, when we are defining something, we'll use this notation. We'll use the letters T and F and capital T for continuous values, and we use N, M, K, L for discrete values. We will use lowercase letters for time domain signals, and we will use the uppercase letters for the transform domain signals. So for example, X of omega x of z. We will use bold face letters to denote vectors or matrices in both time domain and both transform domain. So when we're using bold, we're referring to vectors and matrices. The conjugate complex is symbolized by the star, superscript star. In the transform domain, we will use the superscript star to denote the conjugate only of the coefficients, not including the argument z, and we will use the overline to denote the complete conjugate complex operation, meaning that we are including the argument z. We use e of x as the expectation, which we will use as the average of signal x of n, for example. The down arrow n will symbolize a downsampling by a factor of n. We've seen before the downsampling, we will substitute n by this. And n0 is the phase or the index of the first sample we keep in the downsampling. The upper arrow n is the upsampling by a factor of n, including the insertion of zeros. And the n0 is the phase, so it's the index of the first non-zero sample in the upsampled signal. So we will follow these conventions during all the course and all these tutorials. In the last part of this notebook, we will talk about common types of frequency transforms. Those frequency transforms are fundamental in signal processing. We will be using them in multirate signal processing in the course, in the examples, in our tutorials. And we will start with the discrete-time Fourier transform, the DTFT. So the DTFT is time discrete. So our samples only exist at some sampling time points. We have a sampling interval, capital T. We have a sampling frequency, Fs, that is 1 over the sampling interval. We have infinite signal length from minus infinity to infinity. There is the omega, which is the normalized angular frequency, which is 2 pi times f divided by the sampling frequency. Just remembering that half of the sampling frequency is called the Nyquist frequency. We talked about that before. And it's this transform is continuous in frequency, and it's periodic, so it has a periodicity of 2 pi. And one thing to have in mind is that when one domain is discrete, the other domain is periodic. So we are in time discrete, and that's periodic in frequency. This is also this transform is also invertible, so we have an inverse DTFT. It's given by this formula, and it's very interesting to note and useful that convolution in time domain becomes a multiplication in the DTFT domain, and multiplication is usually much more simple than a convolution. Convolution is mathematically more complicated, and that's the DTFT. Another transform is the discrete Fourier transform. So this transform is still time discrete, but now it's finite in time. So our signal has a fixed length of n samples. We can obtain the DFT as a special case of the DTFT, the discrete-time Fourier transform that we've seen before, if we take our finite signal and we repeat it infinite times in the past and infinite times in the future, making it periodic with a period equals to n. Here is the equation to calculate the DFT, and we note that we have now a discrete frequency index k that goes from 0 to n minus 1, where n is the number of samples. This transform is also invertible, so we have an inverse transform given by this equation. So the DFT is discrete in frequency. It has the frequency index k, that is an integer between 0 to n minus 1. So it is periodic in frequency with period equals to n. And because we're dealing with a periodic signal in time, we have what is called the circular convolution, which is given by this equation here, where mod is the modulus, so it's the remainder of the division by n. Still applies that the circular convolution in time becomes a multiplication in the DFT domain. One of the most important properties in these transforms is to remember that a periodic signal in time leads to discrete frequency, and discrete signal in time leads to periodic spectrum. And we also have this symmetry between time and frequency, so it also holds that the discrete frequency will lead to periodic time, and periodic frequency will lead to discrete time. The discrete cosine transform is a very important block transform, and it can be a bit confusing because it exists many types of the DCT, and each type may have several definitions. So for example, if we take a look at the documentation of the SciPy FFT pack, the DCT documentation, we see that they are offering 4 types of the DCT. They also offer a normalization mode, so it's basically a multiplication by a scaling factor. So they explain here which definition. So there are several definitions of the DCT1. We use the following. So they explain for each type what is the definition they use and what is the normalization mode. So what's the scaling factor they use if you set this normalization mode to ortho. In our case, we are going to use this definition here, which is not defined. There is no inbuilt type, even though it's the type 4 is a different way that we are implementing here. So we see there is this scaling factor square root 2 over n. We can see a shift of 0.5 in the subband index k, in the time index n. We can see this factor here of pi over n, in contrast to a factor of 2 pi over n we've seen in this DFT. So this also will have some implications in terms of the properties of the DCT. We see here the block index m, so we're processing streams, and because we don't have an inbuilt function the way we want, we will adapt the DCT type 3. So we can define the DCT type 4 like this. We initialize, we have we sample up the signal, we take the DCT type 3 with the upsample signal, we use the orthogonal normalization, we multiply it by square root of 2, and we will have what we want. The DCT4, when you multiply by a scaling factor, it can become, the DCT matrix can become orthogonal, and because of the symmetry, the inverse transform becomes exactly like the Fourier transform, and that's our case. We are having here this orthonormal transform, and we have that the inverse DCT4 is exactly like the forward DCT4, so we can use this definition for both the transform, the DCT4, and the inverse transform of the DCT4. The DCT has a different subband density. So as we're talking about this factor pi over n instead of the 2 pi over n, the frequency distance between two neighboring subbands is only half as much as of the DFT. So the DCT provides twice the subband density when compared to the DFT. We now reached the Z-transform. It's one of the most powerful transforms for discrete time. And we can see the Z-transform as a generalization of the discrete time Fourier transform, the DTFT. So if we recall the definition of the DTFT, we see this e to the power of j omega, which is a complex number on the unit circle. But if we replace this complex number on the unit circle by a general complex number that doesn't need to be on the unit circle, we get the Z-transform. So we are replacing e to the power of j omega by z. So in very general terms, the Z-transform is turning a sequence into a polynomial, and we could use sim pi, for example, to transform a sequence into a polynomial. So the Z-transform is more general than the DTFT, and it becomes more powerful because we can compute the Z-transform for unstable signal systems. So that would not be possible for the DTFT because the sum would not converge. We can determine if a system or a signal has damping. So if it lies inside the unit circle, we can see if it's unstable, if there are poles outside the unit circle generating exponentially growing signals. And this is the so-called two-sided Z-transform, but when we are dealing with causal systems that has a starting point in time, we can have the one-sided Z-transform that goes from 0 to infinity. The convolution in time also becomes a multiplication in the Z-domain, so we can take advantage of this. The Z-transform is also invertible, so we have the inverse Z-transform defined by this equation here with this closed contour integral. But when we have causal and stable Z-transform, where all the poles are inside the unit circle, our closed contour can become the unit circle around the origin, and we can set Z to be equal to e to the power of j omega for omega in between 0 to 2 pi. So if we apply some variable substitution, we have that dz over d omega is equal to j times e to the power of j omega, and our Z-transform, inverse Z-transform equation, we can replace z by e to the powers of j omega. dz we replace by this here. The closed contour becomes the normal integral for omega going from 0 to 2 pi. And we have that the Z-transform, the inverse Z-transform for causal stable signals or systems becomes the inverse DTFT, identical to the inverse DTFT. So in practice, all finite length sequences are always causal and stable, and their inverse transform becomes the inverse DTFT, which are the coefficients of the Z-transform polynomial. And we can also use Python to get the coefficients of the Z-transform polynomial. Still remembering that what is periodic in time results in discrete frequency, and the discrete time results into periodic frequency. So in practice, we always will have discrete finite signals, so our frequency domain will be discrete and periodic. Let's now take a look at a few Python examples for Z-transform, and we will start with the Z-transform of an exponentially decaying function defined like this. So we have our signal 0.5 to the power of n for n greater or equal to 0 and 0 elsewhere. When we apply the Z-transform, we will get this summation here, and this summation is equal to this here. So here we can see a pole when z is equal to 0.5. We can see that the z transform converges for all values when the absolute value of z is greater than 0.5, and this is called the region of convergence. And we can see there is a correspondence of an exponential time function to a pole in the z domain. So by looking at the z transform here, we can see that there is a correspondence of an exponential time function and a pole in z domain. So let's see how did we solve this, how do we go from here to here, and let's make use of the geometric sum. So the geometric sum is a summation like this. So let's use a trick. So if we multiply this here by a, so we will have a times s. So a will go inside here, and there will be a summation with a to the power of n plus 1, and this is the same as if we do the summation from n equals to 1 until n, capital N plus 1. So this is the original geometric sum. We multiply this by a, and we will obtain this. So now we will take a times s, which is this, minus s, which is this. So a times s minus s is the same as s times a minus 1. So a times s minus s. And we will have that a times s we had here, and s we have here. So when we take this summation minus this summation, we will end up with a to the power of n, capital N plus 1 minus 1. So if we expand the sum, we will see that all the elements will cancel, because we're taking one minus the other and they will be equal, not for the last element of this sum, which is a to the power of n when n is equal to n plus 1, and here we will have when n is equal to 0. So we have here a to the power of 0, which is this one here. So when we take a times s, this summation, minus s, this summation, we will end up with these two elements here. So if we now divide these elements by a minus 1, we will get that this summation is equal to this divided by this. With some manipulation, we end up like this. So if we multiply up and down by minus 1, we have here. Now, if we replace this a by the z transform here, so this is a summation if all of this is equal to a to the power of n from 0 to infinity. So that's what we're doing here. We're replacing this a here by this, and we get this here. But now we don't want from 0 to n, we want from 0 to infinity. So if we take the limit when n goes to infinity, this factor here will go to 0, and we will end up with this result here, 1 over 1 minus 0.5 times z to the power of minus 1, which is what we've seen here. So we use the geometric sum and this trick here of multiplying by a and then take a times s minus s. So when we do this summation minus this summation, only what is left is this factor here minus this when n is equal to 0 here, and we have our result. We can also use SymPy to solve this. So if we don't want to do all these maths, we can make use of symbolic pi. So we'll be importing symbolic pi. We're defining the symbols, and here we're doing summation 0.5 times z to the power of minus 1 here to the power of n here, going from 0 to n. So there it is. We have here the same result as here. So it's 1 minus 0.5 times z to the power of minus 1 to the power of n plus 1, what we have here, and this here is here. So when if we would do the limit when n goes to infinity, this here goes to 0, and we end up with here. Unfortunately, SymPy has some limitations, and especially when we are dealing with infinity, and it cannot calculate the infinity in this case. So for example, if I change here to infinity, we will have an error. So it just gives me, which is the exactly this here. So we cannot calculate, or if we try to take the limit of this result here when n goes to infinity, we have this result. It doesn't know how to calculate. So there is this limitation, but we can still use up to a certain level. This next example is a simple example, and we want to convolve a signal x with a filter impulse response h using the z-transform. So we know that the convolution in time is equal to a multiplication in the z-domain, so we can make take the z-transform of both the signal and the filter impulse response, multiply in the z-domain, take the inverse z-transform, and we will have the result of the convolution of x with h. So if we take the z-transform of x, we have this polynomial here. The z-transform of h, we have this polynomial here. And we multiply in the z-domain, we have this polynomial here. We take the inverse of z-transform, that we've seen that the inverse of z-transform are the coefficients of this polynomial. So we have this as a result of y. To see if it's correct, the convolution in the time domain, if we use numpy and we convolve x with h, and we have the same result. And also remembering that the convolution is defined by this equation here, we can implement this equation using pure Python without using numpy, and we see that we get the same result. So with this simple example, we showed that the convolution in time corresponds to a multiplication in the z-domain. So we took the z-transform of the sequence x and the filter impulse response h, we multiply them in the z-domain, we take the inverse z-transform, which is just the coefficients of this polynomial, and we have the result, which is the same as convolving the two signals. And that's it for the z-transform. Let's move on. And this is the last topic of this notebook. It is the short-time Fourier transform, widely used in signal processing, and is basically a discrete Fourier transform applied to short blocks of the signal. So we take our signal and we divide it into overlapping blocks. Each block has a length of n, and the overlapping is defined by the hop size m. So here is the analysis equation. So we have m is the block index, and h of n is a window function. In the synthesis part, we have the synthesis equation, and the overlap blocks, they are added up, which is called the overlap add. And also the window has the overlap add property defined here, that it's equals to 1. So we can see the short-time Fourier transform as a filter bank with non-critical sampling. That's usually m is smaller than n, so the overlap, the hop length is smaller than the block length. So in literature you find the window function applied only in the analysis part, but applying it into the synthesis part, it improves the resulting synthesis filters, and it's more similar like usual filter banks. So here's a Python example. So we will take the short time Fourier transform of a sequence from 0 to 31. So this is our signal. We will use the SciPy STFT function. So we're taking a block size of 4, and the default overlap is block size divided by 2. So this will result in 3 subbands downsampled by 2. So here is the result of the short time Fourier transform. We have the frequencies of the FFT subbands. So we have 3 subbands. We have the times of the subband samples, and we can reconstruct by taking the inverse STFT, and we get our signal back. So here's one last example. We will take the short time Fourier transform of an audio file. So I'm loading the audio file with SciPy like we did before, converting it to mono, taking the short time Fourier transform like we did in the previous example by using different parameters, and then I'm plotting using pyplot p-color mesh, and it gives us a spectrogram very similar to the one we had before in the first examples when we used the matplotlib pyplot spectrogram function, and we also used librosa to have the short time Fourier transform and the spectral to plot the spectrogram. So that's it for this notebook. We've seen uniform and non-uniform filter banks, and then we went through many frequency transforms that we will be using during the course and in all these Jupyter Notebooks tutorials. And that's it. See you next time.